Okay, so I am going to be walking through some interview questions that I'm studying right now. This section is called Decrease and Conquer, which is sort of a weird word for binary search. And let's look at this next problem. So the next problem is given a sorted bit array of integers and target value, find the number in the array that is closest to the target. So this is just sounds like binary search. Pretty much every time that you see sorted array, a lot of times it's going to be binary search. If there are two numbers tied for the closest value, return the lowest value. That's a good point. I almost missed that. We're looking for log of n, which is binary search this time, and linear space complexity. So our first example here is we're looking for the target 6, and we have 5 and 7 are closest. They're equally close, so we'll return 5. If we have a target of 8, which is not within the bounds, we're going to return the highest number. And I also assume that means if we get a target of -1, then we'll return 1. And here we have an example of 70, which is in between those two. And of course, if we have an array that's 1, 2, and 3, and we get a target of 2, we're going to return 2. So this is essentially binary search. And instead of just checking if we match the target value, we also check if the current value we're on, or essentially if we found a pair where our target is larger than the item on the left and bigger, or sorry, larger than the item on the left and smaller than the item on the right. So if we had to check for here, we know it's 70 is in between these, and we've found our closest value. Essentially, that's kind of like the most important insight. So let's start by implementing kind of binary search, which this looks the same at the beginning for all implementations of binary search. The important part here is going to be doing the check, where we're checking is this all right or not. In this video, we're going to assume that you already know binary search. There's lots of videos on that. Okay, so the first thing we're going to do is we're going to get our middle index, which is going to be left pointer plus right pointer divided by 2. Some people add this up a little bit differently to avoid integer overflow. For the sake of simplicity, I'm going to make this a little bit easier and just take the midpoint between them. So that means our middle value is going to be array middle index. So our first check, of course, should just be, is our middle value equal to our target? We'll get that one out of the way. Our next check should be, is the item to our left smaller than our target, and is the item to our right larger than our target? So left index is equal to middle index minus 1. Oops. Right index is equal to middle index plus 1. And I'm going to add a comment right now to come back and check for off by 1 errors. So if our pointer is, say our pointers are here, that's our left pointer, and our right pointer is here. And of course, if I try to check for this index, I'm going to get an out of bounds error and crash. So I need to come back to here and figure out how to deal with that. Okay, so if the array left index is smaller than equal to a target, I think that's right, and index is bigger than or equal to our target, we found our match. And now we need to figure out which of those, which item is closer. Let's make left value and right value as well. Makes our comparison a little bit easier. So this is, we are inside the range. This is like we're it's kind of a better example. During our binary search, we've now actually we're not going to be in between the range. We will. This would be if our goal index is 67. Let me check. To the left is lesser than. And okay, so we actually don't want to check our item to the right because now we're kind of spread across these three integers. So let's start with just checking the middle index and the index to the left, the value to the left for this example. Let me think about this for a second. Okay, so I'm just going to go ahead. I don't think this is quite the right solution, but I'm just going to go ahead with only checking for the value to the left because we can only kind of compare two pairs at once. So if left value is less than or equal to the target, and middle value is greater than or equal to the target, then we're within a range. And now we need to check which one is smaller. This may be correct. So now we need to see if the left value is closer or middle value is closer. So we take the absolute value difference between those two positions. So left distance is going to be equal to absolute of left value minus target, and right distance is absolute value of middle value minus target. If, oops, I'm misspelling there. If left distance is right distances, left distance is less than or equal to right distance, because we had that point earlier. The tied to the closest value between the lowest value. Left distance is less than or equal to the right distance. We're going to return a left value. The other case is that the right distance is smaller than the left distance, so else we're going to return left, or sorry, right value. Okay, so that gives us the case where we're in the middle. I'm going to bring this array down here with us to make this a little bit easier. To see. And I'm going to remove some of these items. I'm not sure why I had these ports either. Okay. I don't have a right value anymore. I only have a middle value. Okay, so that's only if we find ourselves in a situation like this where we're looking for 6, and I happen to land on 7. It's in between these. Before we go through the other base cases, like when the target is, in this example, maybe 15, it's not included. Before we get to that step, let's handle the pointer changes. So if we start with this example, our first index check is going to be at index 3, because our left pointer is going to be at 0. Our right pointer is going to be the count of the array, which is 6. So 0 plus 6 divided by 2 is going to be 3. 0, 1, 2, 3. So we're going to start at this spot. We're going to check if the middle value is less than our target, then we know for sure that our target is not going to be in here in the beginning, because this is sorted. So if middle value is less than the target, then we can sort of essentially wall off these items by moving our left pointer to this position. So middle value is less than the target, then left pointer equals our middle index. If the middle value is greater than the target, which would be maybe we are working on some different array that is like this. Then we need to wall off this item. And so we are going to set the right pointer with the middle index. And this actually should be combined between else if because the middle value is neither less than the target or more than the target. It is the target. And so we're just going to return middle value. And we're already doing this check here, so we don't want to double up on that actually. Let's just set it less than or equal to the target for the sake of making the compiler happy. Okay. So I think this does help us, or this does handle this example, but it does not help us for arrays like this second array, where our target is not contained in the array. So I think if we keep on decreasing and increasing our pointers, eventually this while loop will finish, and since we haven't found a value at that point. This doesn't feel like a very good algorithmic way of solving the problem, but a way we can solve the problem is simply we go through the while loop, we don't find a pair of integers where our target is in the middle of it, then we check if the last item, the target is larger than the last item, and if that's the case, we return the last item, and if it's smaller than the first item, then we return that. So we have to draw that first equals the first and last is the last. And of course, if we don't have a first or last, it means we have an empty array. Because we have to return an integer, not an optional integer, then we're just going to fatal error in this case. I'm not saying it's the right use case for your problem, but in this case, we're using a not optional integer. If the target is less than the first, less than or equal to the first, return first, else. If the target is greater than or equal to the last, return the last. Now, it doesn't fit any of these, then I think we're gonna fail error. I'm quite sure this is not the right solution. This should be able to be done without fatal erroring. But let's try our examples that were given up here and see how our solution does. You can see here that I had to fail error on a different question. Okay. First is this array, the target of 6. This is a target of 8. And this is a target of 70. So let's try our method for all of them and see if any of these are correct. We want this to be set to minimum. Great. Let's see how this goes. We are fatal erroring down here. Okay, there we go. 5, 3, 72. Wow. Okay, those are all correct. I didn't see that coming. Okay. What are some other edge cases that I'm not thinking of? Let's try something that is all the target value except for the beginning and the end. So one thing I feel weird about is like what happens if we're at this point? Is that going to give us the correct value here? Let's see. Closest value for it's 5. Now that's going to be correct because the first value it's going to try is 5. This is kind of where I've gotten the most value of interviewing is really once the method's already been written, really thinking hard about different edge cases or ways it can break. So let's change this so that we still have this group of all the 5s, but the first index we try is not 5. Oh, okay, here's something that I did not go back to. I'm not checking for this out of bounds error. So if we have, I think if we have an array that's where everything is less than, everything is greater than our target, we're going to get a crash. Okay, so let's try 100, 101, 102. Our target is still 5. We're going to get a crash here. Boom. Okay. So what is happening is we have a left pointer. Sorry, the left pointer here, right pointer here. We're going to try 101. 101 is greater than our target, so we're going to move our right pointer to here. We had 0 and 1 together, and we divide it, we're going to get 1 again. I'm sorry, we're going to get 0. 0 and 1 divided by 2 is 0.5. Integers in Swift always round down. So 1.9 is not rounded to 2. 1.9 rounds to 1. So then we're going to try, then our pointers are both on 100. And so I wonder if this can be alleviated by changing this to be less than or equal to. No, this is correct. So what do I do whenever let's print out the values of left pointer and right pointer. And I'm going to comment out these method calls so we're not cluttering it up. And let's add a few more items in here. Okay. Left pointer is 0. Right pointer is 5. It's right. And the right pointer is set to 2. So we're starting out. We start out here. And the closest we get to a middle index is at this point. Our target is still less than 102. So then we're going to move to here. Right, and that's when we're doing the middle index is going to be equal to 0. So actually, we can just guard for this here. This is something that we kind of check for at this point. Well, we can guard for it here. So guard that the right pointer is not equal to 0. we know that if we're still if our middle index, we know that if we've already gone all the way to the first item, that the first item is going to be the closest one. So whether the middle index does not equal 0. If it does, we can just go ahead and return array 0, because if our left pointer is at 0 and our right pointer is at 1, and we've already determined that this is larger than our target, then we know that it's going to be our first item. Great. Next video, I'll go and figure out why this number of ones test is crashing. I wrote this on an iPad, and I guess it wasn't good.